got to hit the formula. All right, so if you got the percent composition, then you can make an assumption right to derive information, necessary information. And we're going to talk about that. So to derive necessary info, sometimes you have to make an assumption about a given mass or something like that. So if we got percent composition, we can work backwards. And we can retroactively derive the mass. All right, we can retroactively derive mass by working backwards, right? So in this particular example, we're going to talk about, we have a sample gas and it has a percent composition of, and I'm not writing out all the words, but we'll get the gist of the problem. Percent composition is 27.29% carbon, and then the other part is 72.71% oxygen, right? So the question is, what is the empirical formula? So again, let me write this out, we're going to take a step back and look at what we have versus what we need. Because that's always how you approach solving a problem. Look at what they give you and look at what you need and figure out a way to derive what you don't have so you can get to what you need. So what is the empirical formula? So all we have is the percent composition, but we know that percent composition is based on what? Can anybody help us with that? What is the percent composition normally based on? In other words, is it based on a mass or is it based on moles? What is it based on? Under normal circumstances.
Mass.
It's normally based on the mass. Very good. So with that being said, this is where the assumption comes in. So we can assume, right, that this sample, because it has to be 100% total, is 100 grams. Right? Assume it's 100 grams. And because we know now that it's 100 grams, we can say that, oh, if it's 100 grams, that means that there are 27.29 grams of carbon and 72.71 grams of oxygen. Now we're in the clear. Is that right? Because now we have a number we can work with to determine empirical formula, because in order to do that, you need moles. But you can't get moles from those percentages, but you can get moles from grams. Is that right? So now we can get the number of moles, which is, how do we set this up now? These are what? These are our given masses. So now all we need to do is set this up by finding out what number of moles, right, each one of those represents. So let's see, was it 27.29 grams divided by what are we going to use for carbon? Because it's the given mass over the atomic mass, is that right? So what are we going to use for carbon to determine the number of moles?
12.
Okay, 12.01 grams per mole for carbon. And then for oxygen, it's going to be 72.71 grams divided by 16.0 grams per mole for oxygen. All right. What do you have? For carbon? Break out my little bootleg. All right. Anybody got it yet? Anybody have 2.27 moles for carbon?
That's what I got.
All right. And for oxygen, 4.54 moles, right? So now we can take these numbers, plug them in, because remember the empirical formula for this particular compound is going to be CX and then OY. But we know what these numbers are, right? So we can just put them in. So C 2.24, O 4.54, and then just divide by the smallest number. Everything goes back to the original process once we figure out how to get those grams, right? So this is going to be CO2. That's the empirical formula. So the question was really talking about fermentation. So most of the time, if you're doing a fermentation, there's going to be some evolution of carbon dioxide gas, right? In conversion of some sugar into ethanol. All right. Normally the sugar is glucose. All right. Let's do another example like this. Still dealing with I can move this over. Still dealing with percent composition. That's not. I'll just put it on another sheet. All right, so let's do one more example like this. So let's say I give you a compound. So this is again the second example of using percent composition to determine empirical formula, right? Normally, again, when you have a percent composition, the first step is to assume the total mass of the sample is 100, because your percentages are going to have to add up to 100. So we have a sample that is 40% carbon, 6.71% hydrogen, and then 53.28% oxygen. All right. So again, we want to know the empirical formula. And you know, for the empirical formula, you have to have moles of each one of those elements. You need the number of moles of each one. All right. So again, with an example like this, we can make the assumption that the sample is 100 grams. So what that means is what? Somebody tell me how many grams of carbon you have in this sample.
40.
Okay, 40 grams of carbon. And then we'll just go ahead and, right, this is the given mass divided by the atomic mass. All right, and then by the same token, 6.71 grams hydrogen divided by, right, 1.008 grams per mole. And for oxygen, we'll set that up the same way, 53.28 grams of oxygen divided by 16.0 grams per mole is oxygen. Somebody calculate those real quick, each one of them. If you notice too here, this is a three, this formula has 3 terms in it. It doesn't matter. We're still gonna follow the same process. Anybody got the carbon yet?
I got 3.331.
Okay, so 3.331 moles of carbon. Okay, I'm with you. What about hydrogen?
6.68.
All right, and then oxygen.
3.33.
So if we write this out, and we can round this one, go ahead and round this down to 3.33. So we'll write this out, CHO, and then we'll put the carbon in first, which is 3.33, 6.66, and 3.33. Let's hurry up and divide this. All right, so this is all going to be divided by that. So we left with what? CH2O. Is that right? And at this point, we understand that we don't write out the subscript 1.
Yeah, that's right.
All right, cool. So let's take this a step further. We know how to calculate empirical formula from given masses. We know how to calculate empirical formula from percent composition by assuming that the sample to be 100 grams. So now we're going to use the empirical formula to calculate the molecular formula. So let's do that. All right, so we're going to use the empirical formula to calculate the molecular formula. And so the way we derive and there's a difference. Remember, there's a difference. The empirical formula, remember, is the reduced form. It's the reduced form of the molecular formula, if you remember that. So it doesn't tell you the exact number of atoms present, but the relative number. Right? The exact number has to be derived experimentally, but we can figure out the empirical formula based on the molecular formula. We can figure that out, right? So what we'll have to do is figure out the number of formula units. And I'll explain what that means shortly. right? So to find the molecular formula, we need to find what we call the number of formula units. And that is going to be determined by the molar mass of a compound divided by the empirical formula mass, or formula mass. Let me not just say mass because it's not a mass. Right, so I'm going to take the formula mass of the empirical formula and use that to divide the total molar mass, and that's going to give us the number of formula units, which I can then take and multiply through the empirical formula to find the molecular formula. So this is going to be so it's the let's just say this is the empirical formula right here, and this is the number of formula units. Right, so when we distribute this through, that's going to give us the molecular formula. So it's the EF right? That's the basic calculation to get the molecular formula. It's the empirical formula times the number of formula units. Right, and that's going to get us to the molecular formula. All right, so the best way to do this is just to do it. So we have an example that we're going to do with nicotine. So we know the example gives us a sample of nicotine. All right. And it has a percent composition of 74.02 grams of carbon, 8.710. I'm sorry, not grams, percent, my bad. 8.710%. You know, we're going to convert this into grams though at some point, so we can get the number of moles. And then 17.27% nitrogen. All right. So now this is the percent composition. We're going to use that to calculate the empirical formula at some point, right? The other piece of information that's given in this example is that there are 40.57 grams, the sample of nicotine, and that equates to 0.25 moles. So now we have everything we need to solve this question or solve this problem. Because the way we're gonna, and then the question asks, what is the molecular formula? So we got a percent composition. That's what we have. We have a mass of nicotine and the number of moles that mass represents. And then in order to calculate the molecular formula, remember it is the molar mass divided by the empirical formula mass. Right, so let's put that over here. So it's the molar mass of the compound divided by right, and that's gonna give us those formula units that we can use to figure out what the empirical formula is, right? All right. So now, what would you do first? You have all this information. You have your percent composition. You have your, you have enough information to calculate the molar mass of nicotine. What would you do first?
Convert the percentages.
Okay, so you want to do the empirical formula first. All right, I'm with you. We could do that. Let's find the empirical formula. This sounds like a lot, and it's convoluted, but it's really not that bad of a process because everything that we're doing, we already know how to do, right? So again, we got all these percentages. We can assume 100 grams of nicotine to find the empirical formula, right? So there's going to be 74.02 grams of carbon divided by 12.01 grams per mole. We already have seen this. Then it'll be 8.710 grams of hydrogen divided by 1.008 grams per mole. And then the other part of that calculation is going to be for nitrogen. And that's going to be 17.27, 17.27 grams divided by 14 grams per mole for nitrogen. Can we get those calculations real quick? One person do each one. Any questions about how we're able to go directly to this calculation if we're looking for the empirical formula, right? The reason we're able to do that is because we got the percentages up here from the percent composition. So if we're looking for empirical formula and we don't have the masses, we can just use the percent composition as the mass because if we assume the sample to be 100 grams. All right, anybody got the first one? 74.02 divided by 12.01. I got that 6.06 moles of, I'm sorry, 6.16 moles of carbon. And then for hydrogen, there's going to be 8.64 moles of hydrogen. And then for nitrogen, it can be 1.23. Anybody get, are these numbers matching up with what you've calculated?
Yeah, that's what I got.
All right. So so we're going to take these numbers now and find the empirical formula, which will be, we're just going to write them out. C H N, and then we'll put these numbers in. So 6.16, 1.23, and then 8.6. 8.64. And then we're going to divide everything by what? Which one of these we're going to divide by for the empirical formula?
1.23.
The smallest one. All right, so 1.23, good. All right. Somebody tell me what you have. Anybody got that?
The first one I got, oh yeah, you got it.
All right. Go ahead. You can still say it. You got C5 for your first one?
Yes, I definitely saw 5.
All right. And then H7 and then N1, right?
Yes.
All right, cool. So this is our empirical formula. All right. So we can use this now because, again, let's go back to our equation. We need the empirical formula, molar mass. And then we need the molar mass of the compound. Once we get those two numbers, we can figure out this number, and then we can finish this problem, right? So we got our empirical formula. What would the mass be for the molar mass? How would we do that? Molar mass or molecular weight?
Wouldn't you like multiply the original masses with like the number that they have? It's like 5 times for carbon. Yeah.
Come on. Finish it up. I like it. You sound real confident.
And then for hydrogen, 7 times 1.008. And then nitrogen is just by itself. So you do 1 times mass and then equal all that and then add them all together. And then
add them all together. That's what we're doing. Yes. Thank you. So this is going to be 60.05 grams per mole. This is going to be 7.056 grams per mole. And then this is going to be 14 grams per mole. And then we take the sum of that, which for the sake of time, I'm going to just go ahead and give it to you, 81.106 grams per mole. So this is my molar mass of my empirical formula, which is what I need in my denominator, right? Now, how do I get the molar mass of the actual compound? Right, let's go back up to what they gave us. They said in the problem, I'm saying they like it's some esoteric group that sent a message, but they say here, 40.57 grams is the same as 0.25 moles of nicotine. Right, so let's do that. So we found the empirical formula. We found the empirical formula molar mass. Now we need to find the molar mass of the compound. So the molar mass of nicotine. All right, and in order to do that, we can take those numbers that they gave us in the beginning and just divide them, because remember, molar mass is grams per mole. So we're going to say 40.57 grams divided by 0. Make sure I got this right, 0.25 moles. Everybody following that? Grams per mole gives me molar mass. Right, or molecular weight, whichever. All those terms are interchangeable. So can somebody calculate that real quick?
$162.4 0.3.
We'll take it grams per mole. So that's the molar mass of nicotine itself. The total, it's the same way we calculated the empirical formula molar mass, right? And we're going to find out what the actual molecular formula is now. So how do we do that? So the final step, and this is a long problem, but it's shorter when you think about what we've actually done. I'm gonna go back and recap it too. So we're gonna take the molecular or the molar mass divided by the empirical formula molar mass, right? Which we already calculated. So the molar mass of nicotine was 162.3 grams per mole. And then we're going to divide that by 81.1, let's say 11 grams per mole. And then what do we get for our formula units?
Two.
Right, so this number right here is formula units. Right, so all we're going to do now, we know what the empirical formula is. So that's the final step, is to distribute the formula unit, the number of formula units through the empirical formula. So we're going to take that, what was it, C5H7N? Is that right?
Yes.
So let me back up because I want to make sure we understand what we're doing. So we're going to take this, the empirical formula, and then this is the number of formula units that we just calculated. So we're going to say C5H7N. We're going to put a 2 here, and we're going to distribute that through the whole thing. This is how we get our molecular formula. Right? So the molecular formula is actually going to be C10, H14, N2. Is that right? All right, questions about that? Any questions about that? All right, let me pull up nicotine, the structure, so you can see, we can match this up. All right, so for this problem, what we did, it gave us percent composition, and it gave us a way to find the molar mass. That's all we need, because if we got percent composition, we can figure out the empirical formula. If we got the molar mass and the empirical formula, we can figure out the number of formula units. Once we do that, it's just distribution. That number of formula units distributed through the entire empirical formula, boom, molecular formula. All right, let me pull up nicotine on the screen right there. Find the structure for it. Boom, here we go. So this is, I gotta share. I gotta do a new share. Hold up. Can y'all see that? So this is nicotine. Let's see if we can count up the carbon. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Yes. Remember, we talked about this. Everywhere two things come together, two lines come together, right? That is a carbon, unless there's another atom there. So that's 10 carbons. You see the nitrogen right here and the nitrogen right here. So that's 2 nitrogens, right? And then you see also on each one of these carbons in this ring, 1, 2, 3, well, on 4 of them, there's 1 hydrogen. So that's 4 hydrogens. That's 5. There are 2 on each one of these carbons. So 6, 7, 8, 9, 10, 11. And then there's 3 on the end of this carbon, right? I'm going to write this structure out and write out all the atoms. And then we'll stop there. Let me write it in the notes and then I'll illustrate it that way. Come on, Russell, tighten up. Time is of the essence. All right, so let me go back to my iPad. I'm gonna knock this out and then we'll be done. But I think it's really, really important to understand like the connection with all of this stuff, because once you understand the molecular formula and how to, if you know the formula, you can figure out the molar mass. If you know the molar mass, you can figure out the masses of the elements. You can figure out the empirical formula. So that's like you can maneuver back and forth between all these different pieces of information. All right, so that's that. Let me fix that up. Looks kind of sloppy. All right, so then we got double bonds in here. Boom, like that. Come on, Russell. Here. And again, every one of these carbons has 1 hydrogen on it. All of these are hydrogens. There are 2 hydrogens on this carbon. The key is to, and I'm giving you a little organic right now, but the key is that every carbon can form 4 bonds. So when it's bonded to another atom covalently and it's not charged, right, it's understood that there are 4 bonds to it. So like for this one, right here, you see how it's got a bond right here and 1 right here? That's 2 of your bonds taken up. So the other 2 have to be hydrogen. All right, so this is H, H, and H. So you can count it now. So C, let's do the H's first. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then I missed this one. 14 hydrogens, and then the carbons you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And the nitrogens you can see are 2, 1 and 2. So that is C10, H14, and 2. All right. The thing about this molecular formula is that there can be other compounds with the same formula, right? Those are called isomers, constitutional isomers. You got the same formula but a different structure. You can have that can be hundreds and hundreds of compounds that have this molecular formula. But for this structure right here, which is nicotine, right, this is the formula for it. But there are other isomers that exist that might have the exact same formula. But we ain't gonna worry about that part yet. That's a whole nother ball of wax. All right, any questions about anything so far? I think that we will finish out this chapter this week, but I don't want to put the pressure of trying to squeeze a test in before spring break, so I'm not going to do that. We will have another quiz though, but we won't have the exam. We'll take it after spring break, even if we have to wait a week after spring break to do it. It's fine with me. I don't want to give it to you right when you come back though, because I don't want to ruin your break and have you studying for an exam the Sunday before you get back. So yeah, we'll do that, and then we'll figure out the date for the next test. But we will have a let me start recording. I don't need all our business.